Hi, everyone. I am Saurabh. I'm an engineer on TensorFlow, and I've been working on a bunch of stuff on TensorFlow 2.0 over the last 2 years, and I'm very excited for this opportunity to present to you some of the things we have been working on and some other stuff that we have added to make TensorFlow even more useful for research. So thank you all for coming. Okay, so first question, why do we have a TensorFlow 2.0? Why wasn't TensorFlow 1 good enough? So when TensorFlow started like a few years back, and even before at Disbelief, the goal was to build like a very extensible and very scalable system on which you could run like train and serve very large neural networks. So for that, the graph-based methodology was perfect because we could optimize everything away as much as we wanted. But as our user base grew and lots of new kinds of research started using TensorFlow, for example, RL, we realized that this graph-based paradigm wasn't perfect and like it wasn't very usable. You often had to like jump in and out of this graph mode to do a lot of things. Also, there's a lot of new accelerators that came up, and now you like rarely run your models on single machines, and it's not always straightforward to scale your models from single machines to multiple machines or clusters and things like that. So in TensorFlow 2, we have tried to fix some of these things. Okay, so the first thing we have added is eager execution. So when you define a computation in TF1, you build this kind of computation graph you see on the right. And so basically you have this graph with operation nodes and they are connected with data edges and control edges. And so basically you get these kinds of graph tensors and you get these kinds of graph tensors, and then you have to build a session object, which is your bridge between your symbolic representation to your computation. In TF2, you do not have to build these graph tensors. As soon as you define an operation, you get back a tensor with a concrete numerical values. This is great for debugging and So one obvious benefit you can see is in TensorFlow's input pipeline. So TF data is TensorFlow's functional kind of API for like loading your data, pre-processing it, and using it for training your models. In TF1, when you have to use the input pipeline, you sort of create an iterator object, and then you call iterator.getNext, and then each time you compute this tensor, you get a new entry from a data set. In TF2, when you build a dataset object, it's like a regular Python iterable. So you can iterate over it using a regular Python for loop. Okay, so eager execution is great. It helps you a lot with debugging, but there are very obvious performance benefits to using a graph-based model because you can do a lot of optimizations if you have like full visibility over your computation. So for that, we have added TF function. The TF function allows you to convert the same computation that you have in your eager mode to run it as a graph. So for example, you have this extremely simple model just for illustration, which has a single LSTM cell. And then if you want to run this subpart of your computation as a graph, you can just throw in the TF function decorator. And then in this particular example, it runs 2x faster. So the speed up really depends on what kind of model you have. So if you have a model with like lots of small nodes, then wrapping them as a graph gives you a lot of speed up. But if you like try to have like an adversarial example where you have like a single node with large computation, you might not see much benefit because the overheads of creating functions and running them is high. But I think that's not that common. So usually you should see substantial speed up. Okay, so functions in TensorFlow are polymorphic, which means that you can call a function with values of different types and shapes. And each time you do that, we have to retrace the function. So it's basically convert your function from Python to graph again for each new kind of shape and type. And that can often be expensive, so I'll show you how you can avoid that. And right now, there are still certain corner cases where we can do better, but we don't. So in those cases, we raise warnings and tell you, hey, something is wrong. Maybe you can do this other thing, which will make your function tracing, multiple function tracings go away. So here's an example of type polymorphism. So you have this function $x, which basically does x plus x. You can call it with an integer, a float, or a string. And you can also call it with different shapes of values. For example, you call it here with a scalar, and then you can call it again with a vector. But as I mentioned earlier, now every time you call it with a value of a different shape, this function gets retraced. So you build the graph. So that is expensive. So you can avoid that by explicitly providing an input signature to your function that defines a shape and a type for your tensor. And then each time you run, we don't retrace it, we just make sure that the value you're providing is at least as specific as the shape in your signature. Another cool thing that comes with TF function is autograph, which basically converts your Python control flow into graph control flow. So when you are in eager mode, you obviously want to use Python control flow to do a lot of your computations. And if you run the same thing in graph mode, it will lead to a very inefficient graph if you imagine unrolling all the computation multiple times. So what autograph does is converts these kinds of for loops into graph level control flow like tf.while loop. And it's also smart enough to understand that, say, you have a break statement, it will update the condition to check for these things. So you don't have to change your mental model when you're moving from eager mode to graph mode. But this is not perfect. For example, you still see something called tf.tensorArray, which is TensorFlow's list data structure. In Python, you would expect to use normal lists, and that is something we are looking into supporting over the coming months. Another thing that has bugged people in TF1 is side effect ordering. So side effecting operations are those which, when called, change some underlying state but don't have an outgoing data edge. For example, if you have a variable and you assign a value to a variable, it just changes the state of your variable, but you don't have an outgoing edge from that node to depend on. So imagine if this function did not have a TF function, you would expect the assignment to happen first, and then you do the modulus check, and then you perform the assign again. But if you express this as a graph, since there is no data edge from the assignment and basically from the write and the read, these can run in non-deterministic order. So this has often bugged people in TF1, and you have to manually add control dependencies using TF.control dependencies and things like that. In TF function, we track anything that can depend on its predecessors, and we make sure we add the minimum necessary set of control edges so that all your stateful operations run in the same order. This does not mean everything will run in the program order, because that will be very inefficient. So we make sure that parts that need to run in a sequence and everything else is parallelized. Okay, so here's a very useful guide on TF function, which has a lot more detail. Okay, so in TF1, how we computed gradients was using tf.gradient. So because you had a graph, you can compute the gradient of a graph by doing sort of a backwards pass on the graph and computing a gradient of each node. In TF2, in eager mode, you don't have a graph anymore. So you compute gradient by sort of tracing your operations in the forward pass and then going back through your tape to build your gradient. So the way you use gradient tape is something like this. So imagine you have a tensor x, and then you perform a computation y equals x squared. You have a gradient tape.watch on x, and then to compute the gradient, you just call tape.gradient y with respect to x. So by default, we made a design choice that as soon as you call tape.gradient, we clear all the resources that are held by the tape. So this is for the most common use case in deep learning, where you have a scalar loss and you compute your gradient once, and then you don't need those resources anymore. But if that's not the case for your model, you can define a persistent tape by using persistent equals true, and then you can call gradients as many times, and then you will have to manually clear your tape's resources by using Python delete. You can also use the tape for computing higher order derivatives by nesting them. So in this example, the inner loop computes your forward pass, and then you compute the first order derivative in your inner tf.gradient tape, and then the outer tf.gradient tape is watching your forward pass and the gradient you computed. So now you can compute a gradient over this entire computation to get your second order derivatives. Okay, so in the previous examples, I had these manual watch calls, but those are only meant for non-trainable variable tensors. So if you have any variables in your model, those are automatically tracked. So if you access any variable inside of the context of a tf.gradient tape, we automatically track that, and you can take gradients with respect to those. So in this example, you don't have to track the variables created by your fully connected layers. But in case you don't want to track all your variables, you can pass a special flag called watch access variables equals false. This will say, don't track my variables by default, and I'll tell you what to track, and then you can manually specify which variables you want to track. Okay, so in TF2, we have consolidated on Keras as our top-level API. This does not mean that we are getting rid of all our low-level APIs. You still have access to everything, but Keras provides a lot of nice things. For example, it allows you to track your variables and provides you a nice hierarchy to save your models and then ways to visualize them and things like that. So there are various ways of using Keras. So this is the most simple way of using Keras. You define a sequential model and then you just add layers in a sequence. Or you can define arbitrary DAGs of models by creating your input layers, and then you create your computation, which is a DAG, and then you have your outputs. And then towards the end, you create Keras.model, and then you specify your inputs and outputs. You can also define custom layers using this kind of format where you have a build method which defines your weights and a call method which defines your computation. So you don't have to always create your weights in the build method. You could do that in the constructor as well, but this is required for cases where your weights depend on the input shape, which is often the case, for example, in dense layers. You can also use a subclassing API where each layer has multiple sub-layers which are referenced inside it. And then if you need even more functionality, you can subclass model, which has additional methods for fit and compile, which is basically to run a bit to train and to do inference on your model. So once you have defined your model, which is like encapsulates your computation and your weights, you use compile and fit. So compile, basically you provide compile your optimizer and your loss is already there in the model. So basically it computes your gradient graph and it prepares your model so that now you can train it and then you can do inference over it. And you can use the high-level model.fit API, which basically performs the training, and it has a bunch of these useful callbacks that you provide. For example, you can provide an early stopping callback which says, hey, watch my validation accuracy, and if that doesn't change for a while, just stop training. Or you can provide TensorBoard, which is like TensorFlow's like visualization toolkit, and then you can create a callback with a log directory where all your summaries and all your losses will be logged. Or you can specify a model checkpointing callback, which will basically periodically checkpoint your model so that you don't lose your work if you get preempted. And you can write your own callbacks as well. If you don't want to use the high-level model.fit API, or say you're not subclassing TF Keras model and you're like just using regular layers, or even not even Keras, but even lower-level TensorFlow APIs, you can use the tf.gradient tape to do your training. So you run your model under the tf.gradient tape, you compute the gradients, you update your metrics manually, and you can apply your gradients manually as well. Okay, so I mentioned about performance earlier. So for making it easy to run your models in a distributed setting, we have been working on this tf.distribute API. This comes with a bunch of distribution strategies which allow you to basically run your models under different configurations without changing your code too much. So one example of a distribution strategy is this TF distribute mirrored strategy. This is used when you say want to run your model on a single machine with multiple GPUs. And how this does this is basically replicates your model and your variables on each device, and then it uses something called all reduce to basically keep all your variables in sync. So I'll give you an example of an all reduce algorithm. So here's a ring reduce all reduce algorithm where like your GPUs are arranged in a ring. So in this case, each GPU shares its set of tensors with the next one in the ring, and then they go around in a loop. So in like 2 iterations, each GPU has all the tensors from all of the GPUs. So now they have full information to compute a consistent gradient update to apply to its set of variables. I must also point out that these all reduce algorithms are supposed to be network efficient. So a lot of hardware vendors provide their own custom implementations. So for example, in TF distribute, we use the Nickel library from NVIDIA. Okay, so how do you use tf.distribute? So you have your model code like this. You just throw in these 2 lines of code. You create the mirrored strategy and you create a context manager. And all of our layers and Keras models are aware of these contexts, and then they make sure they're replicated in the right way so you don't have to do anything else. Okay, another example is multi-worker mirrored strategy, which does the same thing as mirrored strategy, but now it allows you to run on multiple workers, each of which can have multiple GPUs. And then we have the parameter server strategy, which was used in like old style TF trading, where like you have a parameter server where you keep your large weights, for example, your embeddings, and you want to do sparse lookups and you don't want to use a device memory for doing that. There's also TPU strategy, but Bruce will cover that in the next talk, so I've skipped that. Okay, so here's some links to learn more. I would especially recommend checking out the TF distribute with custom training loops example, which is really nice. Okay, so for those of you who are not familiar, TensorBoard is the visualization tool for TensorFlow. It allows you to visualize all your loss curves, your image summaries, your graphs. I think we recently added a bunch of support for visualizing the performance of your model. And you can also do 3D visualizations and lots of stuff. So it's very useful if you're using TensorFlow. And the way to use TensorBoard is by using this TensorBoard callback, which writes your logs to a particular directory, and then you can start up TensorBoard in your browser, or you can. Another way of using TensorBoard, if you're not using Kyra, is to define this file writer, which basically says, hey, write all my logs to this directory. You create a context manager for it, and then every time you call this TF summary scalar, it writes your summaries to the default context manager file writer. Okay, so here's a link to learn more about TensorBoard. Okay, so yeah, I still have time. So these are some advanced features that we have been working on in TensorFlow, which are largely research focused. I'm very excited to be sharing here. One of the things we have been working on is tf.vectorized map. So this is like tf.map function, or if you're not familiar with tf.map function, imagine your Python map, which basically applies a function to sub-elements of your tensor, or like a list of tensors, and it does this like serially. So like your function will only apply to a particular slice of your tensor. But this is like highly inefficient. Like there's often opportunity for like batching these things so that you don't perform like single element computation, which are very expensive on like GPUs, for example. So one motivating example is this one. As you can see, if you have a for loop where you do like element-wise multiplications over slices of two tensors A and B, you can equivalently write it as C equals A dot B, where the star is the element-wise multiplication. There are often much more complicated cases which are harder to handle, and when you have like a sort of a graph built for a single, like a bunch of computations together which are built for element-wise operations, it's harder to convert this entire thing into a batch computation. Another example is if you're like me and you like doing single element gathers and you just want it to work for a batch of stuff, you can use TF Vectorized Map, and it works much faster than using TF Map function. Another place where TF Vectorized Map has been used is for computing, for example, gradients. So if you don't want batch aggregated gradients and you would rather have, for example, gradients, you can use TF.Vectorized Map. And in this example, which is very simple, it has just one dense layer, TF.Vectorized Map is 2x faster than TF map function. And this is not just something experimental. We use TF Vectorized Map for computing Jacobians in our gradient tape API. Okay, and yeah, I think so. The support for TF Vectorized Map is not 100%, but it supports, I think, a large chunk of TF's API. So like, I think as of making this slide, it supports like 200 operations. Okay. So another cool thing is tf.custom-gradient. So this allows you to specify a custom gradient function for any Python forward function you have. For example, say for any reason you have a non-differentiable forward function fn, but in your backward pass, you don't want to drop your gradients. So in that case, you can define this kind of gradient pass-through function, which basically says, just pass my incoming gradients through instead of dropping them. Another example is if you want to recompute your forward pass when you're doing a gradient. So if you're concerned about the peak memory usage of your model and you don't want to keep the activations from your forward pass around, you can define this custom gradient function which recomputes your forward function when you're doing a derivative and then uses those activations for the gradient pass. So you basically have a trade-off between performance and memory. Another pretty useful thing is when you want to stabilize a gradient. So if you have this example where you have a log 1 plus x and you take like a naive gradient through this, you will end up with an x power 1 plus x, which will give you a nan at like even moderately large values of x. So you can rewrite it as a custom gradient where you say, hey, just have my gradient to be 1 minus 1 over 1 plus x, which will not give you nans and work as expected. Okay, so another thing we have been working on is forward mode differentiation. So contrast this with the backward modes. In backward mode, you start with the y's and then you apply a chain rule backwards. In forward mode, you start at the top, you start with tangents or derivatives with respect to your axis, and then you work downwards. So this is not in the public API yet, but I think it will land very soon. This basically computes your Jacobian vector product instead of your VGPs. And so this is, I think this is not very useful for the regular single loss neural nets where you just want to compute the first order derivatives. But if you have like say a function which has like multiple y's and a single x, or if you want to compute Hessians or something, this is as efficient as computing a regular backprop, but it takes much lesser memory because this forward propagates a gradient, so it does not need to keep the intermediates around. And we also have added tf.robs. So this is a way of like directly accessing the low-level operations that are available in TensorFlow. So say you're building a library and you really care about using certain operation and you don't want to rely on TF's high-level API, which could swap out these low-level operations under the hood. You can directly use tf.robs. There are some caveats here. I think like you always need to use keyword arguments and things like that, but you have this flexibility if you need. Yeah, and then there's a lot of other stuff going on like Swift for TensorFlow, which is basically provides you language level automatic differentiation and has really nice interop with Python and C, which I would recommend checking it out. And then there's a lot of work going on in MLIR, which is the next gen IR for like upcoming hardware and software platforms for machine learning. And then there's tons and tons of other libraries that have built on top of TensorFlow, which really give TensorFlow its meaning. And yeah, I think a bunch of these have already moved to TensorFlow 2, which is really nice. Okay, that's it. That's all I had. If you're interested in learning more, here's a couple links to guides and tutorials, which have all been updated to TensorFlow 2, so please check it out. And if you have any questions, concerns, or suggestions, please reach out to us on github.com/TensorFlow. Thank you.
So hi, I'm Bruce. I also work at Google, strangely enough. I'm actually a former mathematician, so I kind of moved to this world a long time ago, and now I work on TensorFlow and specifically on TPUs and the APIs around TPUs, and I help internal and external teams sort of move their models from GPUs or CPUs to TPUs. And so we're going to talk a bit about TPUs today, what they're used for, and also tell you a bit about this TFRC, our program where you can get free access, and show you how to get it. So here's our agenda. The first thing, what are TPUs, right? Basically, TPUs are our own ML acceleration hardware. Like a GPU, they can be used for accelerating all your computations, well, most of your computations for your ML models. And they were designed from the ground up to make basically large-scale training possible. I mean, if you look at GPUs just happen to be the hardware which seemed to work right for ML, but they weren't designed for ML from the ground up, right? They were designed to, push pixels to graphics cards so people could play games. It just happened that worked well for machine learning somehow. So TPUs were designed to only do ML, right? Basically, we can do things like map models and more complicated operations very fast and we can do them on with multiple machines, all communicating really well, really quickly. So these are available now. I mean, we have some different versions of TPUs, which I'll talk about, and they're kind of all available now by cloud. So if you have a lot of money, you can purchase them. Or, if you're a researcher, I say you can get these free GPUs we offer to try it out. And we hope that you'll use them and sort of give us feedback and see how they work. So, I mean, here's the problem we had, right? Because Google as a whole was doing a lot of work on CPUs. Basically, we were training models, and we were using hundreds of CPUs, thousands of CPUs. I think some extremely large percentage of Google's compute was spent, training machine learning models on CPU. And, well, because of Moore's law, and then Moore's law is ending, we see that the speed we get for new CPUs is not increasing as fast as it was before. And so the choice we had was basically to say, well, our ML models also get much bigger as well, right? If you look here, you have our simple models back in 2013 or even older than that. And then nowadays we have these new models like our AlphaGo models. You have OpenAI's, Dodo models. So that's OpenAI, right? I always forget. Anyway. There's all these huge models which now have billions of parameters and take petaflops of compute every day. So in fact, our ML usage is outpacing our CPU growth. This is a big problem, right? So the question is, how can we get trained bigger, more modern models quickly at a cost-effective manner? And so that's basically what we tried to do. We said, okay, what can we do? We can increase parallelism, so we can train over more machines, or we can increase specialization, basically. And we did both of these. So TPUs are an answer to both of these. We have a specialized chip. It can compute, all the chips can communicate together over a custom network, so they're really, really fast in that sense, and they're also designed for ML from the ground up. So our two types of chips we have, our two sort of designs we have, and you're going to ask me why they're called V2 and V3 when I say there's two of them, but happen to V1. So V1 is something we're going to talk about, but no, V1 is not publicly available. It's an older design. It was one of our first chips. It was inference only. And so the only thing that we have externally are V2 and V3, which can be used both for training and for inference. And so if you look at these sort of specifications, basically one of these TPU boards here is roughly equivalent to 4 GPUs. So each of these chips is roughly the equivalent of a GPU, but the cost is about, I would say, something like a half or a quarter of the cost. So for us, it's way more efficient and, well, it's more powerful. So this means that you have an option now for TPUs of, rather than having to go out and buy, like, say, 8 GPUs if you want to train a huge model, which might cost you, I don't know, like $20,000, you can now sort of, well, pay a fraction of that cost on Google Cloud to train the same models. And just to have an idea of what these kind of look like, I should point it back here. If you want to, there's a lot of great details here on this link. It's the system architecture for TPUs on our cloud thing, or on our cloud website. You can see basically a huge amount of information about how these machines are put together, and how they connect together. You can see pictures of them in the data center, so you can sort of understand physically how they're laid out. And it's kind of, I don't know, I think it's pretty impressive. The basic layout of the chips looks like this, and this influences kind of some of the designs of the models, or how quickly or what sort of things you can do with models. So basically, our TPU V2 chip, basically on each of those single chips, there's 2 computing cores. Each of the cores has one big matrix multiply unit, which can effectively multiply a 128 by 128 floating point matrix at a time. So this means that effectively the TPU was designed really around multiples of 128. So if you're running a TPU model, you can often actually round up your dense layers or all your tensors and things like this to multiples of 128 for free. So this basically means that, so if you have a small model, you maybe only have 64, you're only using a width of 64 somewhere, just double that to 128, you'll get more parameters, and the compute time really won't go up, because basically what we're having to do is if you give us a 64 wide vector, we're having to pad up to 128 to begin with. So you're kind of wasting cycles. And this TPU v3 chip, which is just coming online now in cloud, has more map model units, so it's twice as fast, and also has more memory, so more space for your parameters on the chips themselves. So I wanted to talk a bit about how people are using TPUs nowadays. Like what are people doing? So here's 3 examples of models which people have trained on TPUs, some internal and some external. So the first thing, I think, one of the first things announced was, you might recall, I don't know, 6 months ago, there was this whole thing where OpenAI announced the GPT-2 model, and then they said, hey, we can't release this because it's too powerful, and people might use it to, I don't know, create spam on the internet. But basically, I think it's totally released now, finally, and we actually helped them train that model on TPUs. We used basically 128 chips. So if you looked at those computer boards you saw there, that's 32 of those computer boards all networked together on computers, and we trained this giant model. I think this model had billions of parameters, and we used a system. In that case, we didn't use TF 2.0 because 2.0 wasn't available at that point in time. For that one, we used something called Mesh TensorFlow, and Mesh TensorFlow, if you can find documentation online, is a way of sort of doing model parallelism rather than data parallelism when you're training on multiple machines. Another example, as was more recently announced, was we did some work with the Mayo Clinic. And so Mayo Clinic is pretty interested in taking models where you have these giant 3-dimensional images from CT scans. So, giant seems small. Like if you think 256 by 256 by 256, that doesn't seem that high resolution. But for them, that's pretty huge. Prior to this, when they were running on GPUs, they could only train their image segmentation models on 128 by 128 by 128 images. And so by scaling this up onto TPUs, we were able to give them a model which trained faster than GPUs, trained on larger images, got better accuracy because of that, because you have larger images, so you can see more. You guys know why, and it was cheaper for them to train. So it's a win-win-win. You get a more accurate model because you have more parameters, it trains faster, and it's cheaper to train. So for them, they were kind of really happy with this. And moreover, to say, we've even actually pushed this even further. We've pushed this, and we've actually managed to train models on 512 by 512 by 512 images. So those are actually kind of spectacularly large when you think about the amount of memory each image takes. Right? So when you're training this model, using a batch size of 1. Right? It's like you can't get around that. As another example of, let's say, large models, was this model BERT, which maybe you might have heard of. I think it was announced some months ago from some Google researchers, but it was a model specifically designed around TPUs. The model architecture was designed to say, this is something which works well on TPUs, this works fast on TPUs, and we got basically, a good model which trained really quickly, and now so far we can actually train this entire model in 76 minutes. So we've gotten the training time down really huge amount by using TPUs, by using these large-scale TPU computations. And as an aside, I think we looked at the paper submissions, I think, for iClear, and we think there's like 200 papers which mention BERT. Like, why are there so many BERT variations? We don't understand. People seem to love this. I don't know why. Another thing we do is, because we know there's problems around TPUs, we might say, okay, sure, you go to a tutorial and somebody tells you, I can run MNIST on a TPU. Congratulations. Of course we know you can run simple models on TPUs, right? How do you actually run complicated models on TPUs? And so we've actually made our goal for ourselves on GitHub to provide you a wide range of free of models which in 2.0, which work and train basically at the same speed the TF1 models do, or even faster. And we can use those, if you are interested, as a basis for your own models. You can take one of these models, check it out, rip out the internal code, and plug your own thing in, or modify them, add layers, I don't know, who knows what you want to do. But so far what we have is, okay, we have BERT, we have transformer model, general transformer model, XLNet, ResNet, and MNIST. Okay, once again, who cares? Save MNIST. But these are all working right now in 2.0 on TPUs if you run them. And moreover, we're going to basically have in this repository more models like GPT-2 and more image models like the SufficientNet and MNASNet and other transformer and object detection models. We're just going to keep on updating this as new models come in, because we want to sort of provide you guys with some examples of what you can do with TPUs. So I want to do a brief discussion about how you can actually use TPUs with TEEF 2.0. So the basic idea is going to be around this idea of distribution strategies, which we briefly discussed earlier. So what's going to happen is, what you're going to do is you're going to log into the Google Cloud, once you have your free TPUs, you'll log into the Google Cloud website, you'll open up the Cloud Console, you'll type in this cTPU up, and as I say, you should use this argument TF version nightly to get all the latest bug fixes. Generally that should work, but sometimes it might be busted. We apologize when that happens, but generally it should work properly. And so our advice is to use distribution strategies. And the idea of distribution strategies is that the same code is supposed to work on CPUs, on GPUs, and on TPUs. All you have to do is swap out the strategy. So in this case, what I'm doing is I'm creating this thing called TPU strategy. You notice that it's in ts.distribute.experimental. Things are still in flux. But basically, you create one of these objects, and if you look at the tutorials online for cloud that tell you how to create one of these, you look at the code that we showed earlier, you create one of these, and then basically what you do is you create your model, you create your optimizer, you create any metrics you want in the scope of the strategy, and then basically anything you do in this model will run on the TPU. And the next big difference is that when you're using distributed data, we generally advise you to use these tfdata.datasets API, because it helps us understand, our APIs understand, what your data looks like and what sort of operations you're applying to it. And with that, we can then take your piece of data and we can split it out and make your data set run on all the individual machines which are having KPUs. Because what's actually happening behind the scenes here, just so you know what's going on, is you saw that tray, or that PCB with those big fans and radiators and those 4 TPU chips on it. Each of those is connected to an actual physical machine. And so effectively, we need to run a copy of this data set on each physical machine, so each machine on the CPU can run your data set, do all the CPU operations which are necessary to let's say, process that data set, and then pass the data to the GPU. So this API lets us take your data set as you defined it, and then essentially instantiate it remotely on all the different machines which have the TPUs on them. And so what you do is you then create an iterator from that, and now you have this thing which we call a distributed data set. You also have to define your loss, and interestingly enough, you don't have to do this inside the scope. So all this stuff here is outside the scope I had here, is with strategy.scope. All you have to do is define these 3 things in that scope, your metrics, your optimizer, and your model itself. Everything else can be defined outside of the scope if you want. So you don't have to worry too much about that. The one thing we're going to note here is that we're going to advise you to use a custom training loop. That's what I'll talk about in a moment. With a custom training loop, we've made some decisions with the API which might be a little different from what you're expecting. It's different from what TF version 1 did. TF version 1, when you had distributed training with something like TPU estimator, it would always take your loss and divide it by the global batch size, so you got the average loss of your global batch. With these custom training loops in TF2, we've made the decision that you have the control. So because you have the control, you have to remember to divide your loss by the global batch size. So that's one caveat that people have found a little annoying in moving from TFV1 to TFV2. So this is basically what a custom training loop looks like. What we're going to define a single function which trains a single step. And what we do is we define this function called training step, and the key thing is that we define it with this decorator called TF function. So what does TF function do? TF function tells TensorFlow that this function is actually a graph. So you express your function in Python, but then TensorFlow traces this function and produces a graph behind the scenes to actually run. And we need to do that because we need to somehow transmit your function to all the different machines which have TPUs on them and run it. And it's just much easier to make a graph, which is what TensorFlow understands natively, from your function, and then transmit that instead. And so inside this training step, what we have is we have a secondary function. This is what we call my TPU step. So it's hard to see here. I apologize for the color of the comment. But basically, everything inside this TPU step function is just going to be run on the TPU. So anything outside of it will be run on the CPU, and everything inside will be run on the TPU. And so we do the exact same sort of things that we talked about earlier with 2.0. You take your inputs from the model, you create your gradient tape, you compute your model, the model function on those inputs, you get your output, you compute your loss. Notice here, I divide by my global batch size, and you compute your gradients, you apply your optimizer, and then let's say I have a metric here for my loss, I put my metric for my loss, and the key thing here is this last statement here, the last statement of the function, strategy and experimental run v2, that's actually what runs your function on the TPU. And or if you're in a different strategy, like if you're in a merge strategy or a multi-worker merge strategy or the parameter server strategy, the same thing applies. So the thing that you have inside that internal step function that you're calling with the experimental run v2, that part is what runs inside the strategy or runs remotely on all the machines. Everything outside of that is just running on your local machine, which is running your Python code. Okay. So that's what your training step looks like, and then what do you do? Well, this is what you do. You just run that step many times. You run it multiple times. You pass in. Whoops! I realized there's a typo there. I forgot to actually pass the data into the training step. Let's see. Did I? Yes, I did. Okay. I'm supposed to pass the iterator. You might have noticed here I created this distributed iterator. I'm supposed to pass that in to here to this training step. I apologize. These things happen, I guess. And also I typed the word epic. Well, wonderful. And you can print out your epics, and basically this training loop is running on your host machine, but it's dispatching the graph to run on the remote TPUs instantaneously as you're running it. And then it's only actually when we actually ask for this value of this. So what you'll notice when you try to do this is these steps will run really fast. In fact, they'll run so fast it's unbelievable because they're getting executed asynchronously. We asynchronously dispatch the TPU computations, and the annoyance is that you will have the final statement, it'll stop, it'll pause until it gets the values back for the training loss, and then output them. So just as another word of warning, don't time, if you're using TPUs with 2.0, you don't want to time your training steps by putting a, let's say, timer around each step, because it won't be very useful. What you want to do is you want to put a timer around the outer loop and then divide by the number of steps, because basically it'll block, getting the TPU execution will block until you get the result back. Okay. So that's pretty simple. I want to give some general advice about TPUs and things to avoid or things that make you slow, because of course there's things that make you slow, right? So the things you want to avoid are tensors that change shape each batch. We technically support this, but what's going to happen is you will be forced to have what's called a recompilation and a retracing of your step function every step that your batch size changes. So this will put a huge overhead, which you don't want to pay. So TPUs, you generally want to keep the size of your tensors the same for each step. The other thing you generally want to avoid inside that TPU function are the TPU step are things which print or deal with strings or write to files. Things that kind of are natively, like you wouldn't think run on a custom piece of hardware. Like, you can avoid this. You can actually enable this thing called soft placement, and we will actually dig into your graph, pull out those functions which don't run on TPU, and place them on the CPU again. Except this is slow, so you will notice a big speed hit if you try to enable this and have prints in the middle of your step. Now, I'll point out that the way kind of around this, if you're debugging things, is to do one of two things. Is to either switch your TPU strategy and use like the merge strategy and run a CPU, because then you can print and do all your normal, let's say, print debugging you might want to do to make sure a model is behaving correctly. Or what you can do actually is you can actually return anything from these functions. So I could return something from my TPU step, and then it'll be the return value of this experimental run v2, and then I can return that from my training step, and then I would see that value here on my host where my Python was running. So you can return values, and that's another way of inspecting your model, inspecting the stuff which is being run on TPU. And as I mentioned before, TPUs generally perform things which are multiples of 128. So you're almost often freely able to round up at least one of your dimensions there to a multiple of 128. Yes. Very good. Okay. So, yes. So there's two options with summary writers with TFlow 2.0. You either can set the soft placement, or you can return your summary from the inner step and write it after the experimental run v2 call. So you're just writing it on the CPU. We kind of handled that for you behind the scenes often with this TPU estimator, which was the V1 API. Whereas, with the V2 API, you have to do a little more of this work yourself. But you can either do this soft placement, and it works. We definitely have models internally which use this and train fine. You just expect a small slowdown due to the transfer back. And you also have to worry, like another thing you have to worry about with TPUs, if you're going to do these sort of things, is are you transferring all the tensors back to the central machine, which is running? Or are you running this so there's some inherent problem, because let's say you have 100 physical hosts running this program, and now you want this tensor back and you want to transfer it back to the host which is running the Python program. You now have to incur the cost of the entire data transfer back to that host. So sometimes you can do tricks like, for instance, only transfer back the summaries from host 1, host 0. And that gets you your summary, and is much faster than getting it from all the hosts. So some general advice here. There's some information on the TFRC. It's this Tensorflow TFRC, if you want to learn more about it. If you want more than just those free 5 TPUs that we're offering with the Mila code, you can actually apply if you have a larger project in mind. You can apply it to this program, and they will, if you succeed, they can give you maybe hundreds of TPUs if you have some large model that you have some huge desire to train. But our advice is to maybe get some experience with the free TPUs with the Mila code first, to see how they work with your setup, and are they compatible with how you want to program them, and before you maybe apply for a larger grant. And in general, other documents on cloud TPUs, and of course our GitHub with our models, and I guess the custom training loop stuff, which was already mentioned earlier. So I have a few more minutes. Are there any specific questions? Well, I'll of course answer things later, and if you want to have questions, privately, we're happy to answer them as well. Yes.
Hi everyone. Sorry for the small delays. I think we are ready to get started. So in the previous presentations, I had an introduction to, and I want to share with you how this can accelerate our research with a concrete example. So I'm Wisdom, and I'm here at Mila. I've been using TensorFlow for the past 2 and TPUs for the past year as beneficiary of the TFRC program. So these are the top things that I think make TensorFlow great for research. The fact that we have eager execution enabled by default, which means we can inspect and debug things. But we can still use graph because they provide speed, scalability, and make your model fast and ready for deployment to the cloud, to the device, and even on the web. And also because of that tight integration with Kyra, an API for machine learning. So I'll be presenting TensorFlow 2.0 from a PyTorch perspective because I'm aware that most of us here at Mila use PyTorch. So I would draw some parallels between TensorFlow 2.0 and PyTorch for research and consider a simple task of video question answering, show how we can distribute training on cloud TPUs, and show you some public resources for researchers. Kyra is a simple API that runs on top of many frameworks, including TensorFlow, Piano, and so on. It's known for its dead simplicity. In the past versions, this came at the cost of flexibility. Simple for the beginners, but hard to customize for researchers like us. And the community was divided between TensorFlow 1.x users that wanted that full flexibility and customized the layers, and using the previous Kyra's API for simple feed-forward neural network. But now both TensorFlow and Kyra have improved a lot, and Kyra now provides, as presented in the previous presentations, 3 styles for creating our models. So the sequential for simple feed-forward neural networks of single inputs and single outputs. The functional API, which appears very simple, is powerful enough for most of our use cases from my experience. And it's very fun that you can use it to compose any arbitrary graph topologies you want. And obviously you can subclass a model, implement your constructor and your custom forward pass. So with that tight integration, you still gain the benefit of TensorFlow as that robust and flexible model, but you can think of it as with now a cleaner API on top of it. And it's good that Keras is now the default high-level API for training models with TensorFlow. So it's now the time to draw some parallels comparisons between TensorFlow 2.0 and PyTorch. So that's how you declare tensors with PyTorch, and that's how you would do it with TensorFlow. So these are the basics. And so those tensors are constants. So the way you will want to declare a mutable tensor, like the weight of a neural network, for instance, will be by using tf.variable. So this tells TensorFlow that this variable would change states across, let's say, the training of your model. And it exposes some operations like assigning the new value, adding from that value, adding to that value, or subtracting from it, as you would do, for instance, in a training update of stochastic gradient descent. So the previous slides already showed how to compute gradients using TensorFlow. So I'm not going to repeat it. So this is, for instance, how you would do it with PyTorch. This is a concrete example with the cross entropy loss. That clear enough? Should I increase it? All right, so here we compute the loss, and with the backward pass, the gradient is available here. So that's how you would do it. Now, with TensorFlow, you open a tape, start watching variables, and outside of the tape, you can retrieve the gradients of that loss with respect to this variable. All right, so I prepared a very simple example we can use to illustrate this. This will be task of video question answering, where you have a video, a sequence of frames, and then a question, and we would like to implement a model that can produce a probability distribution of all the possible answers to the question given the video. So the architecture can look like this. So we have a sequence of frames, and we can use a CNN to extract the visual features from them and model the sequence using an LSTM. And the question is a sequence of tokens, so obviously we need to retrieve the word embeddings and use an LSTM to model to have a summary of that question. And we can concatenate them and have a couple of dense layers on top to classify. So obviously we are researchers, and there are many ways we can complicate this. So here, for instance, rather than having an LSTM, I can, if my CNN is a pre-trained ResNet, for instance, take the last average pooling layer, and I have another pooling on top of it. Since the sequence of frames can be arbitrary, very large, I can also combine only the early and final frames. And for the question, I can also use a transformer rather than an LSTM. And there are also many ways I can use a bidirectional LSTM here as well. right? I can also use a theme generator that would take the question embedding as input and generate the gamma beta values that we can use to modulate the CNN visual feature maps. And since the last average pooling layer of a model like resonance, for instance, will return vectors here. So here we have a sequence of vectors. We can use this as the query of an attention model also to attend to these features. But for the sake of this demo, I will stick with this simple architecture. And here I will show you how you can quickly implement that in Colab. How many of you know Colab and use it? All right, that's great. So here I'm importing resonant model from Kyra. So that's where I instantiate it. And I'm retrieving pre-trained weights on ImageNet. So I think it's already downloaded, so it won't take much time. And in this particular case, I don't want to retrain the CNN model, so I can mark it as not trainable. And so the input to this resonant model is supposed to be a batch and the dimension of each frame. But here we have the sequence, right? This is the number of frames we have. So one trick can be to multiply, to combine these two axes, the batch and the sequence length here, and give it to the CNN and reshape the tensor later. But another way you can quickly do it also is by using a time distributed wrapper, which will give this independently to the CNN for each of the time steps. So the time distributed would take this axis by default as the time axis, and this is good for us. So on top of the frame features, we implement a bidirectional LSTM. And you can see this is the shape of the features. So resonates returns a vector of this size, and we have 128 of them. And this is the output after the LSTM. This is because it's a bidirectional, so we are concatenating the outputs, the hidden state from both directions. And that's how we process the question. So the question is a sequence of integer indices corresponding to the tokens in the vocabulary. And obviously we'll have an embedding layer. So this vocabulary size and the dimension of each embedding, and a bidirectional LSTM on top of it to return a vector of this size. So that's where you combine both. And obviously on top of that, you have a couple of dense layers. I like how you can quickly mention an activation inside this, rather than using, for instance, composing a new layer as we do in Pytorch. And that's how you would build a model. So we instantiate it. And this model here, since we are using the functional API, knows that we have two components, one for the question and one for the video, and know that we expect that we have to give two inputs, right? And here we combine it by mentioning, we compile it by specifying the optimizer and the loss. So if I have disconnected because I didn't run some parts of this, yes. Right. Yes, I should have taken a simpler model. Compile again, and hopefully, yeah, it's compiled. Great. So this is the summary of the model, the different layers we have, and we can see the number of trainable parameters. And I like this utility function that plots a graph of the model. Let's see. So you can see here, that's the section for the video, question, time distributed layer here, the LLCM, and so on. And we have the dense layers. So that's a summary of this model. And as mentioned previously, we use the functional API. So that's how the code looks like. But obviously, we can also subclass. As I said before, in my use cases, the functional API can respond to most of our use cases as researchers. But you can also subclass as we do in Pytorch. One mistake people coming from Pytorch usually do when migrating to TensorFlow is to extend tf_keras.model for each block, because they were told that that was the equivalent to nn.module. But this is not true. In fact, TensorFlow has a tf.module class, which is the base class for neural networks. And the keras extend this with tf.keras.layers.layer for blocks that are not the models. And we also have tf.keras.model for a single model that would take some inputs and return an output. So for building blocks that are not the final model, you should extend layers.layer. So this is the same code as before, but now with the subclassing API. So we have this video model that is the CNN and RNN, and this is how you implement your custom forward loop, forward pass. We have the same for the question model, which is also an extension of a layer because it just block inside our model, and the MLP with one hidden layer and the softmax layer. And that's the model that is the keras model that takes the inputs and that instantiate both models. And this is what the forward pass look like. So obviously I can also go ahead and compile this model. All right. So we can compile it as we did before with the functional API. So I want to go ahead and train this model. So for that, I'm generating fake data. So this is the byte size, number of frames, and dimension of each frame. And I'm sampling from random uniform distribution of the pixels. And this is the question. So just some fake data for training. And I can start training with the fits function. So where are we? Oh, okay. All right. Yeah, but there was a little. All right, so the model should be training now. Go back to the slide for the next section. Yeah, it started training. All right. So that's there. Because you can see in Colab, as you already know, that you can select the runtime, and this was a GPU runtime. So I was training here. I'm training on one GPU. I can stop the train. So I'm training on one GPU, but obviously the goal of this is to show how you can distribute this to TPUs. So the previous talks already covered the different distribution strategies, and tf.distribute is what I'm most excited about with TensorFlow 2.0, because I was one of those that used the estimator, and God, they were hard to use and difficult to debug as well. So it's now cool that with just a distribution strategy, you can distribute to different platforms, including GPUs and TPUs. So that's how the same code can run, for instance, on many GPU. You've already heard about the mirror strategy, which is you have a node and multiple GPUs, and each variables of your model will be duplicated across each of the nodes. So each node compute a forward pass, send back the loss, we update the variables and replicate those variables to each node. So we just specify the strategy here, and we should define and compile the model inside that strategy. This tells TensorFlow that this model variable should be replicated across each of the GPU nodes. And this model compile inside the strategy means tells this optimizer that it will have to aggregate gradients from different nodes. So it's important to have them inside the strategy scope. So with that, we can do the same thing as before, and you can model fits outside of the strategy scope. So we have already specified that this will be a distributed training, and we can just start fitting. All right. So, and now I also want to show you how you can train this on TPUs and have another notebook for this. So to train on TPUs, we need to, as shown in just the previous talk, implement a custom training step. This is the function that computes the loss. This is the lab object. We instantiate some metrics. And this is a training step for each core of the TPU. Not each core, each chip, each CPU chip. Will compute this training step. And we open up a gradient computer model and exceed from the tape, get a gradient of the loss with respect to the model trainable variables. And we use those gradients to update the model variables based on this optimizer. And so that was the code that runs on each TPU chip, and that's the code that tells the model to send the training instruction to each of them. So you do that with this experimental function. So we specify the training step, the distributed data sets, and we also specify the reduce operator to use to aggregate the losses. So now we create inside the TPU strategy. I have to mention that this TPU strategy was created. So you would want to do it at the start of your program because this erases the memory of the TPU. So here we are connecting to the cloud CPU cluster to retrieve the TPU. And in order to use this, let's change runtime. Yeah, I have to specify a TPU accelerator here so that I can train it directly inside Colab. And this is boilerplate code to initialize and connect to the TPU, and that's where we instantiate the TPU strategy. So this was created on top of the code. This is the same code. And now inside this TPU strategy, we can implement a custom training loop as we often do in Python and in Pytorch, sorry, and iterate over data sets and call the distributed training step. You would also notice that I specified the tf.function decorator because this does a heavy workload, and I would like to compile it and optimize it. So with this, you can observe up to 3 or 4 times speed up as compared to with eager execution. So that's it for training on TPU. I'm not gonna run this because of time. And the last thing I wanted to share with you is some public resources for us researchers. So everybody loves pre-trained weights, right? So you can go to TF Hub to get access to some pre-trained models. And I'm also very excited about TensorFlow datasets, which is a collection of more than 100, I checked yesterday, pre-processed common datasets we use both for language modeling, object detection, and many tasks. So you will like to use this. And these are some resources to get started with TensorFlow 2.0 for researchers. I used some of these to prepare the slides. Yeah, thank you.
Hi, everyone. My name is Anne. I'm a software engineer at Google, and I'm here to talk about TensorFlow.js. So specifically, I'm going to try to cover 3 topics, which is 1, why would you want to do machine learning with JavaScript? 2, why you would want to use TensorFlow.js to do machine learning with JavaScript. And finally, 3, how people today are using TensorFlow. So why would you want to do machine learning with JavaScript? It's true that there already exists very mature tools for doing machine learning in other languages, like Python. But JavaScript offers some unique advantages over these other languages. And to try to make that case, I want to show you this video of an interactive Google Doodle, which was featured last March in honor of composer JS Bach's 334th birthday. On that day, if you went to google.com, you would have seen some empty staff lines inviting you to compose a simple melody. And once you did, the doodle would create a harmony to go with your melody, resulting in a mini Bach-style chorale. Behind the scenes, we were sending each user's composition through a neural network that generates harmonizing voices based on a seed melody. And if the user's device was powerful enough, and so this is why I'm showing you this video, if the user's device was powerful enough, we would actually run that inference on the client using TensorFlow.js. All in all, that day, TensorFlow.js generated approximately 30 million pieces of music. And not only was it just cool for us to see our library being used by so many people, Google was actually also able to save significant server resources that day by pushing model execution to the client. Which brings me to the first reason for using JavaScript for machine learning, is it reduces server-side costs. And also by saving that round trip to the server, there's potential for reducing latency. Another advantage of running your models client-side is that it better protects user privacy. Suppose you have a model that makes medical diagnoses based on user images. If that model can run entirely on the client, then those user images never have to leave the browser. Or suppose you have a text-based model that analyzes a user's newsfeed in order to suggest relevant content. Users might appreciate not having to send what they're reading to your server for analysis. The other advantage of running your models in a browser is that there's nothing to install. Oh, sorry. Not actually advancing it. Yeah, there's nothing to install. Running a model can be as simple as opening a web page. This makes it possible for your models to reach a much bigger audience. Also, if your model runs in a browser, that means it can access things like the device's camera, microphone, sensors, and other capabilities through standard web APIs. Finally, if you're working on an application that has any sort of web front end, then you might as well use JavaScript for model execution, if it's possible. So what is TensorFlow.js? TensorFlow.js is an open source library we've built for people to deploy, retrain, and author models using JavaScript. The API includes everything from low-level ops such as matrix multiplication or normalization, as well as high-level keras-like constructs, which we call layers. We also offer a library of pre-trained models for common tasks, including image classification, object detection, pose detection, speech detection, and text classification. These models are small, fast, and ready to be used in any web page with just a few lines of code. So, as you can tell by the name, TensorFlow.js is part of the TensorFlow ecosystem. And this diagram presents one way to think about how all the different components of TensorFlow fit together. So if you already use TensorFlow Python, you can think of TensorFlow.js as a deployment target. So you might author your model in Python and then use TensorFlow.js to execute it in a browser or in. We have a converter that we built for this common use case. Our converter takes TensorFlow save models or Keras models and converts them for consumption by TensorFlow.js. Now, I just want to note that as a deployment target, TensorFlow.js, of course, works within browsers and Node, but we've also built custom integrations with native platforms such as WeChat, React Native, and Electron. So before we get into some of the ways people are using TensorFlow.js, I want to talk about performance. We know performance is top of mind for ML application developers, and for that reason, we've worked hard to make our library competitive with native solutions like TF-Lite. This diagram has some numbers for one sort of representative model, MobileNet v2. You can see that TensorFlow.js is comparable to TF-Lite for MacBooks and iPhones for client-side inference. For server-side development, TensorFlow.js actually has roughly the same performance characteristics as TensorFlow, and that's because our node backend forwards execution to TensorFlow, which means that under the hood, we're able to take advantage of the same performance that you might be used to if you already work with TensorFlow Python. And I also want to note that these numbers should only improve. We've been investing heavily in new technologies such as WebGPU, which bring compute shaders to the web, as well as WASM, which promises near-native performance for JavaScript. We've published experimental backends using these technologies, and we're actively evolving them in collaboration with open source contributors, as well as teams from Chrome and. Oh man. Well, so this is supposed to be a screen cap of one of our WeChat apps working. I'll just describe it to you guys. So I want to talk about some of the ways that people are using TensorFlow.js today. This application by L'Oreal lets users virtually try on L'Oreal products, such as different shades of lipstick, before purchasing them through the app. The app uses a lightweight facial landmark detection model that runs on TensorFlow.js. And the way it works is the user can press different colors of lipstick, which you can sort of see, and the lipstick will apply itself to the user's lips on the screen. And I just think it's a cool example of how running a model on device can make for a really nice user experience. Next, I want to talk about how Airbnb is using TensorFlow.js as part of their onboarding experience for new users. So when you create an account with Airbnb, you need to upload a profile picture, and sometimes people will upload something like a passport or which might contain sensitive information that the user wouldn't actually want shown to the world. So to solve this problem, engineers at Airbnb trained a model to recognize government IDs. They converted the model to run in TensorFlow.js, and they baked it into their new user sign-up flow. And this is just another example of how running a model client-side can integrate within a nice user experience. I want to talk about some of the ways that people in the machine learning research community are using TensorFlow.js. And we really love these use cases because TensorFlow.js actually grew out of a research project in trying to tie together the experience of model development more closely with the experience of model visualization, model introspection. So in this screen cap, you would have seen a web application that was developed by some researchers on our, which is a hugely popular language model that's increasingly prevalent in predictive systems. And the way it works is BERT produces these massive vectors to characterize pieces of language. And our team developed a tool to look at how these vectors change given perturbations of the input text. So we ran BERT through our converter and shipped it into this web application using TensorFlow.js. Inference takes around 150 milliseconds, which is not real time, but it's pretty cool to be able to arbitrarily change a piece of input text and see how the vectors update. And what I think it points to is that that TensorFlow.js has the potential to power sort of a new class of interactive model introspection tools. So here's another example. This application is called Manifold, and this is a web app that was developed at Uber Research for comparing model performance. Manifold is designed for ML researchers who want to understand the trade-offs in adopting one particular model over. And the way it works is by clustering the predictions of different models and showing the user how these clusterings compare. Manifold uses TensorFlow.js for k-means clustering and for computing comparison stats between models. And I think this is just another cool example of doing things in the browser that you might naturally think to do with Python. And finally, I just want to highlight the TensorFlow.js community. We launched the library about 1.5 years ago, and since then we've seen significant adoption among JavaScript developers and ML practitioners. We're lucky to be working alongside an active community of open source contributors to continuously be improving the library. And we've also been excited to see a number of projects build on top of our library, such as Base API.js, which detects spatial boundaries, as well as ML5, which teaches machine learning, interactive browser exercises. And that's it. Here's some links to learn more. Thank you so much. And if anyone has any questions, I'll take them. Otherwise, Joseph Cohen, who's a postdoc at the University of Montreal, will talk to you next about his research and some of the ways he's using TensorFlow.js. Thanks.
Thank you for joining today. So I'm going to talk about just X-rays. We look at the diagnostic pipeline in a hospital. We can see that some patient comes in, they get an exam, some visualization happens, and then some expert renders an opinion that could lead towards the diagnosis, or makes a diagnosis based on evidence from some visualization of an X-ray, perhaps. And then this goes on to form a cycle of treating the patient. So this detect, classify component is where AI stands to make a lot of ground and improve healthcare. So in the past, there have been tools that kind of help here, and this is this KDRI, so it's like a kidney donor risk index. And this is a tool that's been around for a long time. It was online on this date, but it's existed for a while as a model that you can run, like a computational model to assist in your decision, right? But now it's on the web. There's the Framingham Heart Study as a risk calculator for your cardiovascular risk, which is now online, so doctors can use it to aid in their diagnosis, right? So it just makes sense for the next step to be just X-ray diagnosis is kind of like a calculator to analyze the radiological findings in an X-ray. Okay, so where is this useful? It says emergency room. So in an emergency room, you have time-limited humans, where AI you can just kind of use computational resources instead of people time to not miss anything and reduce errors and deal with like fatigued doctors that don't want to make mistakes. And kind of not miss anything. You can also use this in rural hospitals. If we had this kind of calculator, where you're so far away from radiologists, kind of getting the knowledge of a radiologist to those areas is very difficult. And maybe there's not a lot of in that region. There's not a lot of resources for radiologists, right? So they just can't have a bunch of remote radiologists. They have to use automation, kind of fill the gap, fill this missing need. Also, rare diseases. So this is something that this project is not doing yet because we need more data. But very rare diseases where doctors are puzzled. This is where a tool would help them, find those like weird features in the images that could be indicative of some diseases. Also, triaging. So you can have people that are not doctors triaging cases that a doctor will see, right? So that the most complicated cases or most dangerous cases are seen first. And this can be done with someone just utilizing this tool, and because every patient is still going to be viewed by a doctor, you don't really have a risk of someone who isn't trained doing this. So you can spread out the workload, right? Because the knowledge can be encapsulated in this tool, right? Instead of just the doctor. Great. So this project has been called NICE by Jan LeCun. So this project is called Chester. It's a funny name because it's a chest and then it's a person. So this is a web delivered tool, right? So all the code is delivered via the web browser, right? So everything is flat files on a server, which makes scaling this almost zero cost, right? Because it's just flat files that can be cached, right? And then all the computation happens in the browser, right? So no data gets sent, right? I mean, I guess this is a TensorFlow JS kind of talk, so this is the goal of this, so, which is important for patient privacy, right? Because a doctor can't just without like a lot of overhead. But if it never leaves the hospital, right, then there's no issue. But getting software installed in the hospital is a pain. And in this case, it's just a web browser, so there is no installation. It's just running it, right? So we really hit all these pain points and make this thing like a viable vector for using these tools, where kind of a lot of other stuff gets in the way of radiologists and doctors getting exposure to deep learning tools, right? And then a big piece of this that wasn't really accounted if you talk about deployments is outlier detection, which I'll go over in a bit. But we want to avoid, processing images of cats, right? This is if someone puts one in, we can't give it we can't find that it has a lung nodule. That would erode the confidence that a doctor would have in these tools, right? So we really need to calibrate them for the domain that they're going to be operating in. Great. So we want to make free tools for everyone. We want to let medical professionals experiment with these tools by just bypassing all the red tape. Show the potential of open data. So this was done using data from the NIH, which is completely open. There's no paperwork that we have to do for like 2 years at a time and waiting for approval. It's just a data set you can just get and work with, right? So this is what works for deep learning. And if deep learning is going to work in healthcare, we need to have a way to encourage deep learning is the way, we have a way to encourage that open data is the way to go if you want to see results, right? Great. And also you can use this tool to teach radiology. And there's probably also a bunch of other use cases that we haven't thought of. Great. So we want to bridge this divide. There's the doctors, and then there are deep learning researchers at Mila, and they're really far away, and no one somewhere in the middle, we expect some magic to happen and make the researchers develop things that the doctors need, right? And I think the classic paradigm people fall to is having companies fill this need, but it seems like that's not working fast enough. So we should just have researchers talk directly to doctors in a way that they can do. Great. So now some TensorFlow.js slides. Right? So the technical kind of piece of this, which I'm not going to go into too much detail, but we need to run DenseNet in the browser, right? And we need to compute it in like 1 second, right? Although it takes 12 seconds for an initial run and then 1 second for each subsequent run of the model. But we can do that with TensorFlow.js. Out of distribution detection, right? So we played with a lot of different techniques. It turns out that autoencoders are just awesome. But if you augment them with a SIM score, right? So it's a structured image similarity. This allows us to perform this task of rejecting, cat pictures and pictures of knees pretty effectively. But there's still a lot of research to do there. All right. So we also want to do visualization. So this tool will show you a saliency map of where the model predicted like which pixels were used in the prediction, right? So we could do that by shipping like another model that just specifically computes the gradients for a prediction. But that's annoying and maybe not as versatile. And then we have to ship more weights to the client because here we're actually shipping 150 megabytes of weights to the client's browser and then hoping that everything caches properly so they can use this. But we don't want to ship too much. So if we could just, so why send special models when we can just use autodiff in the browser, right? So we can compute the gradients right in the browser and make this whole big computation graph, and it's all right in the browser. So it saves a lot of network bandwidth, but also lets us do more versatile things if we want to visualize just specific diseases instead of just like having one model that predicts one gradient map. We can have different kind of configurations. So we have a lot more freedom to do better visualizations. Great. So I'll go over some feedback real quick. So this is the kind of use of this. So it's spiked with some articles. And then we have kind of a constant usage at about 150 users a week. When they spend like about 3 minutes on the site. So it's like people are using this thing. There's been a lot of confrontation on Twitter. I guess there are people that really like this and they're like, oh, this is amazing. We're seeing the future. And then some other people that say, like, this stuff makes mistakes sometimes, therefore we can't trust it, right? And it does make mistakes, but this is the state of the art, and it's just okay. So it's not even that. So like this is where we are in research, and so there's not some magic silver bullet like research that's going to be released, right? We took the state of the art model and put it here. So if doctors don't like it, then we need to do research. We need to do more research to make this thing better, or that's just the maximal amount of information that's in the image, right? So we need to have this discussion more. Great, so there's been a bunch of articles from all over the world, right? So we have like Russia, Japan, Portugal. Great, so the most hype article had this title. This is a good article, but it kind of positioned it in a wrong way that says that we're like the whole thing is going to read X-rays better than doctors, where the only research paper says that this model, and it's not even the one we evaluated, does better in pneumonia prediction when compared directly against doctors. So people have contention about this specific study. But in general, this is not true. We have a long way to go. Sorry. Okay, so some good feedback. So this is like shocked a lot of people. And this is kind of the stuff we want, that people are able to use this and they see it work. They know the limits. They understand what it can do. They get to learn what the errors are that it's going to make, right? So this is important. Great. So there's been a bunch of studies. This is contributed X-rays from a hospital in Japan, where they looked at the performance prediction on cases that they had, kind of studied the use of this. And this is exactly the outcome that we wanted. There's another in-depth study here, where they kind of really go in depth on specific tasks, right? So they want to study a fusion, so they look at an image that has a fusion in it, and then see how well the model can predict this, right? And they find that it works really well in some cases, it doesn't work as well in other cases, and there's a good discussion in this article about like the labels that we're actually using, right, that were defined by the NIH. They might not be the right separation that people would agree on, right? So sometimes people think they should just be the same label, you can't tell them apart, or they should be separate labels, right? So this actually varies between hospitals, and it's like the opinions of hospitals on what are diseases kind of might be a roadblock in deploying medical technology into these hospitals. Great. So I want to thank co-authors. The source code is online here. The system is there. I want to thank everybody. Maybe people are in this room who helped make this possible. And thanks. Questions? So it's like 110,000 X-rays from about 30,000 patients. Multi-hot. Yeah, so we have 0 or all of 14 diseases, 14 radiological findings, yeah. I was shown in Pytorch because like the DenseNet model that is like the state-of-the-art model was used in PyTorch. So we'd play around with it in PyTorch, and then we can kind of convert it through Onyx to TensorFlow and then deploy it. Yeah. So the framework that we have developed, like in there's a bunch of conversion utilities. So you could take something from Kyra, and I think you can already do that. You could take any library that can go through Onyx can like spit out a model that this framework will use and put into a browser and run like this, and then compute gradients. So no matter kind of what you throw in, it'd be robust to all these different configurations.
All right, how's it going, everybody? That is super loud. Awesome. This one? Okay, great. So I will talk quietly. How's it going? I'm Josh from the TensorFlow team. This will be really quick. I just want to maybe take 15 minutes and summarize some of the things that have been said today and point you to a few useful code examples that I hope will be helpful to you. And before we get into that, I just wanted to say a few words about TensorFlow JS, because we just saw two really awesome talks from Anne and Joseph. And if you're not already convinced that ML on the web is maybe the way of the future, I just want to show you a few awesome demos live that really helped convince me this was the way forward. And the reason I wanted to talk about this is when I first heard about TensorFlow JS, I was totally wrong about it. When I heard the idea, I was thinking like, great, like, okay, we're running machine learning in JavaScript, and I'm all about making machine learning accessible to more users, which is great. But, you know, I scratch my head a lot trying to make Python go faster. So I'm like, God, why are we moving to JavaScript? It's going to be slow and terrible. And here are 50 reasons why I was super wrong. So you've already seen we can do interactive ML, which is huge. We can do client-side ML, which is huge. But putting some of those together, like here are a couple amazing things just right off the shelf that are nuts. The Wi-Fi here is actually pretty fast, so I preloaded this just in case, but we don't need it. So this is a model called PoseNet, and it's running live in the browser, and maybe some of you have seen it. And I'm almost certainly going to accidentally destroy the BlueJeans setup, but I'm just going to carefully, horribly point this at y'all. And so I can't see what's happening. So this is not meant for this many people, but already this is nuts, right? So like seeing this, it's immediately apparent that, yeah, doing this in Python would be a nightmare. So another really important takeaway from Joseph's talk, which I'm new to. So obviously you can convert TensorFlow models to run in TensorFlow JS, but Joseph's work was in Pytorch, also converted to run in TensorFlow JS. So this is a big deal. And then, okay, in the same family as PoseNet, there's BodyPix, and this was work out of, I believe, NYU and Google. I'm from New York, so yeah. And this is BodyPix, and I'm not BodyPix. This is a segmentation doohickey. And so this, I won't point at you because it's going to break, but you can see this is doing real-time segmentation. And these models are running really, really fast, and obviously if you switch it to something like MobileNet or whatever, it'll be even quicker. So yeah, so those are two things right off the bat. I will come back to, so obviously Vision has like the best demos and everybody likes Vision and stuff like that, but there's a ton of important work in text. And so probably like the most boring lesson I have to teach when I teach this stuff is like, okay, kids, let's do like sentiment analysis and text classification, which are really important, but people fall asleep. But anyway, the only time I've actually been excited when I've seen text classification is text classification running in the browser, which immediately is more interesting. So here we have some, this is probably like a, I don't know what this is. This is some basic time series model. But anyway, we're doing sentiment analysis. Hey, how's it? So we can say, that movie was great. And we can see it's positive, terrible at the bottom of the screen. So super cool and interactive in real time. So yeah, a lot of value here. Other things that I pulled right out of the bag of demos. I don't think we have time for this since I want to leave a lot of time for Q&A while we have a couple of experts here that really, really know what they're talking about. But you can try this at home. There is a Pac-Man demo. And this is a way to control Pac-Man with the webcam. And basically the idea here, I think there's two different models. I think this one is actually doing transfer learning. And so what it's going to do is to go left or whatever, you just hold down on the mouse and you collect a bunch of training data. So when it awkwardly sees my head looking at you all, it's going to be left. And then let me see if I can fly through this. If I'm not in screen at all, it's going to go up. And then let me just mess up the other two really quickly just so I can show you how this works. So great. And then anyway, you would hit train. And then we've just trained some model on top of probably MobileNet. And then if we hit play, and then I guess if I want to go left and then up, what I'm going to do is just awkwardly have my head right here. And that should send it left as soon as it starts playing. I'm not sure what's going on. It's happening. Something terrible has happened, but anyway, it's probably because I have 15 applications open using the webcam. But anyway, you can check out the Pac-Man game. It's super cool. I've got like a billion things here. Let me kill BodyPix. Well, whatever. It will recognize the gesture and control Pac-Man. So that's super, super cool. Anyway, these things are great with kids. It's also if you're trying to motivate people to learn machine learning. I mean, obviously these are all extremely hard to build, but you can't really do better than Pac-Man. So there's a lot of value there. Okay, so other things, just to summarize some things of what's been said. So TensorFlow 2 is all about ease of use, which is great. But I think from a teaching perspective and also a research perspective, basically what I really like about it is progressive disclosure of complexity. And so basically we have a spectrum, and there's super easy ways to define your model. And that's using things like the sequential model for stacks. It's a wonderful place to start teaching with sequential and fit. Then we have things like functional for DAGs, and then we have subclassing for Chain or PyTorch, full customization, which is really, really nice. And what this means, especially for students in a classroom setting, if you're doing outreach and things like that in your free time, is you can sort of get students up and running and they can make their code work. And as they're ready for more sophisticated concepts, you can expose them when they're helpful. So that's great. And then likewise, when we're training models, the same thing is true. If your model happens to fit into the model.fit training paradigm, awesome, model.fit, and you're done. The other really nice thing about model.fit, it's performant, but it's also easy to maintain. So if you don't need to write a custom training loop every time, don't. And then if you do need to, we have gradient tapes, which, by the way, custom training loops work the same way with sequential models, functional models, subclass models. It doesn't matter. Likewise, model.fit works with all those models as well. Also, if you check out our distributed training tutorials, so by the way, here are the latest resources. So TensorFlow 2 is like 2 weeks old. So I'm used to typing tensorflow.org/beta, but now everything is just at tensorflow.org. So here are the latest resources, not surprisingly. TensorFlow.org, we just got rid of our beta website. TensorFlow.org/tutorials has all the latest tutorials. In case you're new to, well, I'll come back to this. Basically, our resources are divided into tutorials and guides. And the tutorials are basically short examples of common tasks, and the guides over here have more detail and background. So for distributed training, speaking of these different levels of abstraction, we've got distributed training with Keras, and this is probably model.fit. And just like you've seen before, all you need to do distributed training, which I really, really like, is basically adding a with block. And now you have this fancy all reduce, one machine, multiple GPUs training strategy, which is great. And then also you'll see right down the road we have custom training loops. So it's complexity as you need it. And then, just because some people are new to this division, a lot of Google products have this tutorials and guide things. I'm pretty sure it came from Android, or it might have predated that. You'll also find that we have a lot more background on what these different strategies are. Another good resource that I want to point you at right now, in case you're new to it, it's on YouTube. And if you search for, this is my presentation account, so who knows what these recommendations are. If you search for Inside TensorFlow Distributed Training, and this is a new series. Here we go. So basically, these are just, there's a whole bunch of these. This is Josh Levenberg, and he's one of the many engineers working on distributed training. But these are basically low-budget tech talks, and these are internal trainings. And you can see that, it's just some dude with the camera just filming Josh. And Josh will give like a 60-minute deep dive on distributed training. And to be honest, I usually don't watch videos. They're too slow. I look at the transcripts and I read them, or I like to read the slides or the summary. But I've been spending some time watching these because they're a really, really good resource. And there's also one from Francois. It's actually 2 hours. It's just all the details you want to know about exactly what happens when you call model.fit, exactly what happens when you write a custom layer, how layers relate to models, and how you write custom metrics and losses. It's everything. So this is a really, really good resource. Anyway. And these are all targeted towards people of your skill level. So they're serious talks. They have a lot of detail. They're fast. So they're good. And there's a bunch of them. All right. Other resources that I can point you at. We're moving our blog to our own server pretty soon. But the best way to stay informed of what's happening with TensorFlow is we have a blog right now on Medium. And we have a mixture of articles on there. I just spoke with some people that gave talks I really like. They're both from the TensorFlow team, but also the community. If you have work that you think is of interest to the community at large, and you're interested in sharing it, you can shoot me an email. We can take a look at it. By the way, here's my email address. Anyone who's doing teaching or outreach and has any like TensorFlow questions or would like TensorFlow slides, I'm happy to help. Feel free to shoot me a line, drop me a line rather. We have a Twitter. That's where our updates are. And then I wanted to mention more things about the tutorials. So here's sort of the state of where we are. At this point, I know these are a little bit disorganized, but at this point, we have a pretty good bag of stuff. So if you're interested in GANs, and this question came up earlier, and it turns out the person that asked it probably knows way more about GANs than I do. But if you're interested in seeing like, hey, I've heard about this PyTorch style model, but I've never actually seen like a serious implementation, where can I find it? The fastest way is just go to our tutorials, and here's one for CycleGAN, which is awesome. And what's cool is every single tutorial we have on this page is TensorFlow, ready for TensorFlow 2. They all have complete code. So you can download these on GitHub or open them up in Colab, and every single one will run end to end. And I really, really like this because, you know the expression, trust but verify? So whenever somebody tells me, you know, I've seen so much and I've written so much code that worked once and never worked again. And because all our tutorials are runnable end to end, CycleGAN, the tutorials will have these cute pictures at the top, and the code will produce exactly those pictures. So this is great. We also have an enormous collection of models on GitHub. And the main difference is the tutorials are trying to have the minimum-ish amount of code to show the concept. And what you'll find on GitHub is more production quality research code. But that's sort of what we have for you. All right. I know you know a lot of this stuff, so I just want to give you some points that came up. So just a quick slide, and I just stuck some notes on it for you. If you're new to using Keras inside TensorFlow, and TF Keras is the superset of what you might be used to at keras.io. It's the stuff with subclassing and gradient tapes and all that. You should know that if you happen to be using Colab, Colab right now has Keras installed by default, and it has TensorFlow 1 installed by default. And what you need to do is, at the start of your Colab, you need to install TensorFlow 2. The best way to install TensorFlow 2, we have a flag. Let me show you how this looks. So if I open up our CycleGAN tutorial, I scroll down at the top, we have some magic. And so this is just magic for Colab. If you run this, oh God, that's the table of contents. I don't care about that. It's back again. We have magic that you can use at the start of all of our tutorials to install TensorFlow 2. And that will save you from pip installing it. This will just switch the runtime to a different version. So this is great. So that's the fastest way to get going. If you're new to this Keras stuff and you want to try it out, what you don't want to do is import Keras. If you do that inside Colab, you're going to import the reference implementation, which is multi-backend Keras. Basically, what you want is from TensorFlow import Keras. And I see students make this mistake all the time. It's our fault for having Colab set up the way it is. You just want to keep your eyes out for using TensorFlow backend. If you see that there's something wrong with your imports, just copy the imports from our tutorials and you should be good to go. All right, let's see. I will give you guys a choice. So let's do this. So it is now 3:40, so we have 20 minutes left. We can do one of two things. We can take the next 20 minutes for Q&A, or I can point you to some code that you can run just to get familiar with just some of these new TensorFlow 2.0 styles of writing code. I would suggest that we do Q&A because we have experts here, and the truth is the best way to get familiar with TensorFlow 2, go through the tutorials. If you see anything that we can improve, please shoot me an email. I'd really appreciate your feedback. One thing that I'd personally like to do over the next 6 months is, especially for researchers and especially for folks familiar with Pytorch, I'd like to have just Pytorch has a really, really wonderful getting started, with like low-level tensors and gradients and stuff like that. I'd like to have something similar. But if there's content that would be helpful that's missing, please let me know, and we'll try and get it on the website. So basically, if you're new to this stuff and you want to start from a researchy perspective, under the advanced section, I would go through this customization flow, which is really nice. And this will go into the details of tensors and gradients and all that stuff. The guides also are a really good resource. That and Inside TensorFlow is a really, really solid learning journey. For simple educational resources, so this is all very, very light reading. But especially for undergraduates and for folks that want to dive into TensorFlow without really having like a strong math background yet, I have 3 hands-on book recommendations which are really, really good. Hands-on ML from Aurélien Giron is excellent. If you look at this book, you definitely want the second edition. The first edition is good too, but it teaches TensorFlow 1, which you should skip. It is not necessary to learn TensorFlow 1 to learn TensorFlow 2, but if you have, that's really useful foundational knowledge. Deep Learning with Python is the Keras book. It's wonderful for students. I've used it in a couple classes as supplementary reading, and everybody's had a good time with it. And there's a JavaScript version of exactly the same book, which is also really good. All right, so And then basically one diagram that I thought might be helpful too is this is sort of our flow chart of the, or I guess this is like a business school 101 diagram, right? Where it's showing you like the different development styles in TensorFlow, and it's comparing them on these like easy to use versus high level and low level axes. This is sort of the spectrum. And so that's what we're shooting for. And I'm really happy with it so far. So while we have people here, what we can do is stop recording. I'm happy to take like questions recorded, but I want to dive in, especially like for researchers using PyTorch. I'd really like to take the time to understand what can we do to make TensorFlow 2 better suited to your use cases.